Good afternoon, all. Welcome to sixth discussion session of the course Strength of Material course offered by NPTL. The course instructor of this course is Professor Siman Kumar Bhattacharya. He is a professor from IIT Kharagpur. I myself, Asif Raza, I am a teaching assistant. I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. So, because of certain circumstances, this session has been preponed to this date, uh, that is 29th August 2023. So so you guys will find this recorded lecture, and that will help you in solving the assignment number 6. So without any delay, let's start discussing the questions relevant to assignment number 6. Before that, I wanted to say a one question which we discussed in the last session. This was question number 11. The question was, a steel circular cylindrical pressure vessel stores a fluid under high pressure. A strain gauge measures the longitudinal strain of the vessel. The ultimate shear stress in the walls of the vessel is 50 megapascal. At what strain should the pressure be reduced? And Young's modulus and Poisson's ratio values were given. So this is a very good question. So according to the question it says the ultimate shear stress in the walls of the vessel is 50 megapascal. So keeping into that account, yes, it says it's given that ultimate shear stress in the walls of the vessels is that is tau s is equal to 50 megapascal, and for thin cylindrical vessel we know that the shear stress is equal to maximum shear stress would be equal to sigma 1 minus sigma 2 by 2, and in this context uh, hoop stress minus longitudinal stress upon 2, and since hoop stress is twice of longitudinal stress, so that will ultimately give me that longitudinal stress is equal to twice of this uh, ultimate shear stress, and just substituting those values we can get the longitudinal stress values and hoop stress values, and after that we can get the longitudinal strain value by using the formula sigma L upon E minus mu sigma H upon E, and just substitute this formula and we'll get 0.0002. So this has been corrected and uh, uploaded in the notes section, so you guys can check it out. Okay, now moving on to today's session, discussion of questions relevant to assignment number 6. So for this session or for this week, the most important of all is to remember this torsion equation. This torsion equation is the most important thing, where T is the torque applied and its unit would be Newton meter, but I would like to keep it in Newton millimeter. Then J is polar moment of inertia and its unit is millimeter to the power 4. Then J is shear modulus or modulus of rigidity, its unit is Newton per millimeter square or megapascal. Then theta is twist, better to keep it in radian. Then length unit millimeter, and tau is shear stress, its unit Newton per mm square or megapascal. Then R is radius, calculate that's a millimeter. Okay, so it's best to remember this formula, that is T upon J is equal to G theta upon L equal to tau upon R. So this is one equation. So this thing you have to remember, because this would be immensely used for this type of uh, for this topic. And another thing is uh, we can remember is torque or power is equal to 2 times power is equal to torque times omega, where P and uh, omega is equal to 2 pi f, where P is power given by kilowatt and omega is angular frequency, and f is frequency, units in hertz or revolution per second. Okay, so it's best to remember this. The most important one is this one. So okay, let's start discussing the question. So we'll start with basic question first. That is question number 9. So in that thing only, so the question says torsional stiffness can be expressed as, and the options are Gj upon L, Jl upon G, Tr upon J, and Tj upon L. So just now, as we uh, give the torsion equation, that was Tj equal to G theta by L equal to tau upon R. We will use this first two expressions, and that will give me T by J equal to G theta by L, and torsional stiffness is equal to T upon theta, so that will be equal to Gj upon L. Okay, so yeah, the torsional stiffness is this. So consequently, correct option would be option A. Okay. Now moving on to the next question. The question says the stress state at the cross section of a circular shaft subjected to a torque is, and options are combination of bending and shear stresses, only bending stresses, pure shear, or none of this. Uh, so the question asks what is the straight state of the cross section of a circular shaft subjected to a torque, and the correct option is, it's a straightforward, the correct answer is option C, it's a pure shear case. So you can think about this like, yeah, here we are talking about shear only, shear stresses. So this is a case of pure shear. So yeah, it's a direct question. Now let's move on to the next question. Yeah, so we'll just so the question is, a hollow steel shaft has inner and outer radii as 20 mm and 25 mm respectively. It is subjected to a twisting moment of 400 Newton meter. The maximum shear stress in the shaft is. So first thing, we'll note down what all things have been given. So uh, inner radii, di is equal to 20 mm, outer radii d naught is equal to 25 mm. It is subjected to a twisting moment, that is torque is equal to 400 Newton meter. That would be equal to 400 into 10 to the power 3 Newton mm. Okay, so we need to find what would be tau max. Okay, so this is the question. So first thing first, we'll just write the torsion equation. T upon J, G theta by L, tau by R. Okay, now we can see we'll use the first and the last expression of this equation. So that will give me T by J equal to tau by R, and since we want to find tau max, so we can modify this and write tau max upon capital R, and this would be equal to tau max equal to capital R would be equal to T naught D naught by 2 outer radii. Okay, now out of this all thing, tau max would be equal to T D naught by 2J. So out of all this thing, everything has been provided. J is not given, so we need to find what would be my J, that is polar moment of inertia, and that is given by pi d naught 4 minus t ti 4 by 32. Okay, so this will be equal to d naught 25 4 minus ti 20 to the power 4, and let me find this. The pi 25 divided by 30. Okay, one thing to correct, this inner radii, it's not diameter, so it's a given thing is diameter, so I'll just modify this would be inner diameter, outer diameter, and this would be equal to 2 times 20, that would be 40 mm, 2 times 25, that would be 50 mm. So we'll just write here as 50 to the power 4 minus 40 to the power 4. So on calculating, we'll get it would be equal to 36264.9 03 millimeter 4. Okay, now I'll just substitute this in the above expression to get tau max. So tau max would be is 4 into 10 to the power 5 D naught is 50.2 into 362.264.903, and this would be equal to this would be equal to 27.6 Newton per mm square, that is 27.6 megapascal. The correct option would be option D, 27.6 megapascal. Okay, I suggest straightforward use of the formula and substitute that, and we'll get this atomics. Now moving on to the next question. The question is, in a shaft of length 1 meter and a twisting moment of 300 Newton meter is applied, given shear modulus G is equal to 77 gigapascal, and considering the cross section of the shaft to be same as in question 1, the angle of twist per unit length is, so this time, so length is given as 1 meter, that is 1000 mm. Then twisting moment T is given as 300 Newton meter, that would be equal to 3 into 10 to the power 5 Newton millimeter. Then shear modulus is 77 gigapascal, that would be equal to 77 into 10 to the power 3 Newton per mm square. Consider the outer dia is same as above, 50 mm. Inner dia is 40 mm. Okay, we need to find what would be theta, twist per unit length. So twist per unit length, that is theta upon L. So now the torsion equation is T upon J G theta by L tau by R. So now we'll use these two expression and get theta by L. So theta by L would be equal to T by Gj, and with the earlier expression of J, just substitute this first. 3 into 10 to the power 5, G as 77 into 10 to the power 3. Earlier expression we got for J was 362264.903 4. Yeah, so we'll substitute this. Three six 64 point. So we get 1.0754 into 10 to the power minus 5 radian. So we need to find it in degree. and degree. Okay, so that doesn't mean degree per meter. So just convert this. Theta would be equal to 1.0754 into, it's a 10 to the power minus 5 into 10 to the power 3, and this would be equal to 1.0754 into 10 to the power minus 2 radian. We need to convert it into degree, and that would be equal to 1.0754 into 10 to the power minus 2 into 180 upon pi degree, and this would be equal to 0.616 degree. Answer is option D. Okay. Moving on to the next question. So this question number 3 is, a solid circular shaft is expected to transmit 250 kilowatt while turning at 1.5 revolution per second. The allowable shear stress is 45 megapascal. The required diameter of the shaft is. Okay, so first thing first, write everything which is given. So power is provided, that is 250 kilowatt. Uh, okay, I can just convert it into this is equal to 2.5 into 10 to the power 5 watt, or 2.5 into 10 to the power 5 Newton meter per second, and then you can write it as 2.5 into 10 to the power 8 Newton mm per second. Okay. Now revolution is given as, so frequency f is given as 1.5 revolutions per second. Now we can find, and okay, allowable shear stress is given as 45 megapascal, that is 45 Newton per mm square. Now we can find the applied torque is equal to, or we know the expression, power is torque times omega, and that is omega is 2 pi f. So f is equal to T is equal to P upon 2 pi f. Substitute this would be 2.5 into 10 to the power 5, 8 upon 2 pi f is 1.5, and this would be in Newton mm. Okay, now we need to calculate diameter of the shaft. So let us write the torsion equation, that is T by J G theta by L tau by R And uh, since allowable tau is this, mm, first, what would be my J? J, if given diameter of the shaft, let us keep it as D, it would be equal to pi T4 by 32. So let us use the first and the last expression. Uh, that would be T by J equal to tau by R, and T equal to tau J by R is D by 2, that is tau J is pi by 32 D4 T by 2. Again simplify it, tau pi D cube by 16. So this will be equal to D cube is 16 T tau pi. Let us substitute it again. Now D would be equal to 16 T tau pi 1 by 3, and let us substitute all the values. 16 tau is 45 by T is 2.5 into 10 to the power 8 upon 2 pi to 1.5. Yeah, okay. So let us calculate this. Sixteen into 2.5 to 45 divided by. So this comes around 144.26 mm. So roughly we can say our diameter value is 144 mm. That is option A. So yeah, please look into this. If, so this time we had to use the power formula, okay, and then again we had to use the torsion equation. The torsion equation is must, okay, and then easy substitution will give me the required diameter of this question. Now let's move on to the next question. The question is, torsion is applied to a circular shaft in a twist of 3 degrees over a length of 1 meter. The maximum shear stress is induced is 120 megapascal, and modulus of rigidity of the shaft is 80 gigapascal. What is the radius of the shaft in mm? Okay, let's write the things which are already provided. So angle of twist is 3 degree, that can be converted into radian, that is equal to 3 into pi upon 180, that is pi upon 60 radian. Okay, now length is 1 meter, that is 1000 mm. Maximum shear stress tau max is 120 megapascal, 120 Newton per mm square, then modulus of rigidity G is 80 gigapascal, that is 80 into 10 to the power 3 Newton per mm square. You need to find the radius. So, for this kind of question, my polar moment of inertia would be pi d4 by 32, or I can write pi r4 by 2, okay, in mm4. And just let us write the torsion equation. Theta by L tau max by R tau by R. So we are already provided with max value. So we'll use the second and third expression. So just use the second and third expression. That would be 18 to 10 power 3. Theta is pi by 60 upon L. L is 10 to the power 3. That is equal to tau max. Tau max is 120 upon R. Okay, so it's a easy thing. So 10 power 3 goes 60. R would be equal to 120 times 60 divided by 80 times pi, and this would be equal to 42, 43, 30, 30, 230, and 90 upon pi. The correct answer would be option D, 90 upon pi. Okay, so this time we had to use the second and third expression of the torsion equation. Okay. Moving on to the next question again. The diameter. So the question number 5 is, the diameter of a shaft is increased from 30 mm to 60 mm. Okay, so that the diameter of a shaft is increased from 30 mm to 60 mm, all other conditions remaining unchanged. How many times its torque carrying capacity will be increased? And the options are option A 2 times, option B 4 times, option C 8 times, and option D 16 times. So in this question, every conditions been like kept same, except the diameter of the shaft is increased from 30 mm to 60 mm. So we'll write the torsion equation first. Let us write it. So torsion equation is T by J G theta by L tau by R. Okay, so diameter of a shaft is increased from 30 mm to 60 mm. Okay, now for this, let us use the first and the third expression. First and the third expression, that will give me T by J equal to tau by R, and that would be like T equal to tau J by R, and J is like if it's a circular shaft, that is equal to pi by 4, pi by 32, pi d4 by 32, and r is equal to d by 2. That will be like tau uh, pi d4 by 32 t by 2. This would be equal to tau uh, pi tau by 16 dq. So if all other conditions are same, you can see is t is directly proportional to uh, uh, like proportional to d with the power of 3. So uh, if my new diameter, like if diameter increases by 2 times, uh, 30 to 60, okay, let me write. So t is directly proportional to d cube. That means t2 by t1 would be equal to d2 by d1 to the power 3, and d2 is equal to 60 mm, and d1 is equal to 30 mm. So d2 by d1 is equal to 2, implies t2 by t1 is equal to 8. So our torque carrying capacity will increase by 8 times. So correct answer would be option C, 8 times. Okay. So I hope this is okay for you all. In this question, the diameter of the shaft was increased from 30 mm to 60 mm while keeping other conditions same. So we need to find the torque carrying capacity. So for that we use the first and third expression of the torque equation, and we just find how the torque carrying capacity is varying with diameter d, and we find that it's cubic. And so normally, since the diameter increases by 2 times, our torque carrying capacity will increase by 2 cube, that would be equal to 8 times. Okay. Now let's move on to the next question. Okay. So now question number 6. A solid circular shaft of diameter d and length l, fixed at both ends A and B, is subjected to a twisting. So question number 6 is, a solid circular shaft of diameter d and length l, fixed at both ends A and B, is subjected to a twisting moment T at point C, which is at a distance of L by 5 from A. The torsional stress in the parts AC and CB will be, and options are equal. Option B in the ratio 1 is to 4, option C in the ratio 4 is to 1, and option D indeterminate. So let us first draw free body diagram, like what is it the question asking. So we are given with a solid circular shaft like this, which is fixed at both ends A and B. So having a diameter D, okay, circular shaft with diameter D, length L, subjected to twisting moment T. Let us say this at point C, and this has a length L by 5 from A. So this would be automatically equal to 4L by 5 from B. Okay. I hope this is at least question is clear for you all. So this solid circular shaft is fixed at the both ends A and B, and the torsion T, this twisting moment T, is applied at C, and this C is at a distance L by 5 from A. Now we need to find the torsional stresses in the parts AC and CB. Okay. So first thing first, let us write the torsion developed in A is, let me write TA and here as TB. Okay. TATB. According to the question, okay, leave it. Now, torsion equation. Torsion equation is T by J equal to G theta by L equal to tau by R. So according to the question, we need to find torsional stress is tau A upon tau B, that is torsional stress developed at point A upon torsional stress upon point B. So for that we'll use use okay, so since the twist would be the same, that would be same for both since it is fixed, like theta c would be same for both the points, and the shear modulus is same. We'll use the expression 2 and 3, that is G theta by L equal to tau by R, and theta c, theta is equal to theta or I will write if so if I see G is same, R is same, L will change, right? Okay, let me write it properly. Theta would be equal to G tau tau L upon G R. Okay, now theta CA would be equal to theta CB, and that would be equal to tau tau A upon LCA and G upon R, and tau B LCB equal to G upon R. So we need to find tau A upon tau B. that would be equal to LCB upon LCA, and LCB is 4L by 5 while LCA is L by 5. This would be equal to 4 by 1, that is 4:1 is the correct answer. Let's say, yeah, so correct answer is option C, in the ratio 4:1. Okay, I think this question is quite easy. Now we can move on to the next question. Question number 7. As far as I know, this question is already given in, already asked in the assignment 6, so we won't be exactly solving it, but I will give you guys hint how to solve this question. So in the question is find the maximum torque that can be applied safely to a shaft of 300 mm dia. The permissible angle of twist is 1.5 degree in length of 7.5 meter, and the shearing stress is not to exceed 40 megapascal. The modulus of rigidity of the shaft material is 84.4 gigapascal. So you guys need to find what would be my T max. Okay. According to the given question, given with the diameter 100 mm, permissible angle of twist theta max is 1.5 degree, length is 7.5 meter, that is mm, tau max is given is or theta allowable, I would say, 1.5, tau allowable as 40 megapascal. Then Young's modulus of rigidity is 84.4 gigapascal, that is 84.4 into 10 to the power 3 megapascal. Okay, so I won't solve the question directly, but I'll give you guys hint how to solve this. So you guys already know the torsion equation, that is T by J equal to G theta by L tau by R. So what you need to do is first try to use allowable first try to use the allowable theta. So you need to first use these last two expression and then use like theta allowable as the given and find tau. So if tau exceeds tau max, so if tau exceeds, first use theta allowable and find tau. If tau exceeds tau allowable, then theta should be less than theta allowable, and okay, theta should be less than theta allowable, and find t corresponding to this. Okay, else tau would be less than tau allowable. Oh no, then theta should be less than theta allowable. This is then else tau must be less than tau allowable, and find t corresponding to this. Now second, you have to again solve it taking the other way. You use tau allowable value, find theta, and this theta should be less than theta allowable, then just find t corresponding to this, and else theta would be greater than theta allowable. That won't give me the correct answer. So correspondingly, considering both, you guys need to check which of them gives a lesser torque, because that would be my design capacity, and T max would be lesser of those two. Well, okay, I have given you guys a hint. Uh, you may try it and solve this. Okay. Moving on to the next question. So question number 8. Question number 8 is, in a torsion test, the specimen is a hollow shaft with 50 mm external and 30 mm internal diameter. An applied torque of 1.6 kN is found to produce an angular twist of 0.5 degree measured on a length of 0.2 meter of the shaft. Determine Poisson's ratio of the shaft material with the given Young's modulus of elasticity is 200 gigapascal, and the options are option A 0.125, option B 0.225, option C 0.457, option D 0.165. So let us uh, write the given values first. So we are given with the external dia, I'll just write DO as 50 mm, internal dia as 30 mm, and applied torque as 1.6 kilo Newton meter. That would be equal to 1.6 into 10 to the power 6 Newton millimeter. To produce an angular twist of 0.5 degree, that would be equal to 0.5 into pi upon 180 radian, and length is equal to 0.2 meter. That would be kind of 200 mm, and E is equal to 200 gigapascal. That would be kind of 2 into 10 to the power 5 megapascal. So we need to find Poisson's ratio here. Okay, so let us first write the torsion equation, that is T by J G theta by L tau by R. So, what do you think? What would be the which of the expressions would be used to calculate this? So we can see we are given with the twist. We can find polar moment of inertia. We are given with yeah, we are not directly given the shear modulus, but we can find using the Young's modulus and Poisson's ratio, and twist and length is provided. So we'll use the first and second expression of the torsion equation, that is T by J equal to G theta by L, and on simplifying, G can be written as T L upon J theta. that is G is equal to uh, mm, T is 1.6 into 10 power 6, L is 200, J is pi by 32. Okay, let me write it. Uh, uh, so J would be equal to pi by 32 t naught to the power 4 minus t I to the power 4, and this would be equal to pi by 32 d naught is 50 and d is 30. Yeah. Okay, let us calculate this first. Uh, t to the power 4 minus 30 to the power 4 into pi divided by 32, and this is equal to 534,070.75 mm to the power 4. Now G is okay, so G would be equal to T is 1.6 into 10 power 6, L is 200 mm, J is again 534,070.75, and theta is, it was given as 0.5 degree, that would be equal to this amount of radian. Let us calculate this. So this comes out to be 68660 point. Okay, let it be like this: 68660 megapascal. Now this is modulus of rigidity or shear modulus. So this can be written in terms of Young's modulus as mm, E is 2G 1 plus mu. So 1 plus mu would be equal to E upon 2J, and mu would be equal to A upon 2G minus 1. So let's substitute it. E is 2 into 10 to the power 5. This is 68660 into 2 minus 1. So this comes out to be this comes around to be mu is equal to 0.4565 roughly 0.4565. Okay, so let us round it to 3 digits, so you can write mu is equal to 0.457, and The option from all the four is 0.1. Option C, 0.457. I hope it's clear to all. Okay. Yeah, so in the question it was already provided with external dia and internal dia. Torque was provided, angular twist was provided with the length of the section, and we needed to calculate Poisson's ratio while the Young's modulus was already given. So we just need to use the first and second expression of the torsion equation, and additional equation was the expression relation between Young's modulus with shear modulus and Poisson's ratio. That is this expression E is equal to 2g times 1 plus mu. So on easy substitution of the formula, you can directly get the answer, and the answer comes out to be 0.457. So with that, we got the correct option as option C. Moving on to the next question now. So as you can see, this question we have already discussed. This is also discussed. So now question number 11. Question number 11. Question number 11 says a circular rod ABC is fixed at ends A and C. It is subjected to torque T at B such that AB equal to BC equal to L by 2, and the polar moment of inertia of portions AB and BC are 3J and J respectively. If G is the modulus of rigidity, the angle of twist at point P is. Okay. Now let us draw the free body diagram first. So let me draw it. Circles are with torque at point B, A, B, C with length L by 2, and this has a polar moment of inertia as 3J and this as J. That is JAB equal to 3J, JBC is equal to J. If G is the LAB equal to LBC is equal to L by 2, and we need to find what is the angle of twist at P, that is theta B. Okay, so first thing first, we'll just write here TA and here as TP, the reaction torques TATP, and we'll write the torsion equation, that is T by J G theta by L tau by R. So we need to find the angle of twist at point B, and we are given with the torques and polar moment of inertia. So you guys can get the gist that we'll be using the first and second expression of the torsion equation. So with that would be kind of theta would be equal to TL upon GJ. Okay. Now Uh, so theta b, uh, theta ba would be equal to theta bc. Okay, since theta ba would be equal to theta b minus theta a, and this is equal to 0, this would be equal to theta b, while theta bc would be equal to theta b minus theta c. This is also 0, so this is also theta b. Now let's use the expression and substitute it. This would be kind of dba times, or I'll write it, I've been using ab. Okay, I'll just convert here as ba. So dba lba gba jba is equal to dbc lbc gbc jbc. Now lba and lbc are same, so it gets cancelled out. We can write dba as db and dbc as dc. So, that will give me db gba, which is the modulus of residuity, that is gba gbc is equal to g. So this also gets cancelled out. J ba equal to tc jbc. So ta would be equal to tc jbc jba by 3j, tc is j. So this gives me ta equal to 3 tc. So one of the equation, I'll write here 1, this is 2. One more equation is from the torque equilibrium equation. It will come out to be Ta plus Tc is equal to T, and this would be equal to, like using 2, it will, like from 2 and 3, we get 3 Tc plus Tc into T. That means Tc is equal to T by 4, and Ta would be equal to 3T by 4. Okay, then theta b, the question asks theta b. Theta b would be equal to, if I use the expression for theta ba, and that would be equal to tba lba gba and jba. This is ba is 3t by 4, this is l by 2, and jab is 3j, and jb, sorry, this is g and this is 3j. Simplifying it, will give me 3 cancel outs, TL by 8GJ. So let's see if any of the expression matches. Mm, yeah, so option B, TL by 8GJ. And you can see TC would be equal to T by 4 and TA would be equal to 3T by 4. Okay, so we can also cross verify the expression theta B using theta BC, LBC, GBC and JBC. This would be like if substituted, TBC is TC, that is T by 4, and this is L by 2, this is G, and this is J. So this also comes out to be TL by 8GJ. So yeah, so option B is the correct answer. Okay, so in this case, the one more thing which you had to use is the torsion equilibrium equation. That is equation number 3. TA plus TC is equal to T. Okay, moving on to the next question. I hope this question has been resolved. If you guys have any doubt, you can like post it in the discussion forum. I'll try to give answer when I get time. Okay, moving on to the next question. So question number 12 is a prismatic shaft of radius r has built-in ends and is subjected to two externally applied torque as shown in the figure. Given A is 75 cm, B is 125 cm, C is 100 cm. The internal torque in the portion ABC are. Okay, so in the question we are provided with the shaft radius and there is an external torque 12,000 kg per centimeter and 24,000 kg centimeter when applied in the system, and the ends are fixed and the values of A, B, C are given. So we need to find the internal torques in the portion AB, like in this portion, and in this portion. So let us try to calculate this. First let me draw the PD of this. Try to make a bigger one. So we are given with the torque 12,000 kg centimeter, 24,000 kg centimeter, A, B, C. Okay, nothing else. Shaft radius is 2r. So first thing first, well, first draw the end moments or the resisting torques developed in this system due to this applied twisting moments. So let us write at this end as TA and this end as TB. Okay, so we'll consider this as portion A this as uh, O A B C. Okay, now O A B C. Now let us write the torsion equation first, and that is d by j is equal to g theta by L times equals to tau by R. Okay, for this we'll be using expressions first and second, and let us write for the for angle for the angle of twist, that would be equal to PL by GJ. Okay, now if I uh, want to find the rotation or the twist of theta C relative to O, that is theta CO, that would be equal to theta C minus theta O. Okay, and this would be equal to 0 because theta C and theta O both are 0, but theta CO is a cumulative thing, and this would be uh, equal to theta C B plus theta B A plus theta A O, and this is equal to 0. Now just write theta CB with this expression. Okay, so theta CB is what? TCB LCB upon GCB by JCB. Okay, and TCB is TB only. Okay, TB. LCB is length C. GCB is J is same throughout the section, right? So we'll just write G only, and this has J only. Okay. Similarly, for theta PA, it would be equal to T PA L BA GBA JBA, and this would be equal to TB minus of 24,000 times length is P GJ, and similarly theta AO is TAO LAO GAO JAO. This would be equal to TB minus 24,000 minus 12,000 times A upon GJ. Now substitute this in the above, we'll get TBC GJ plus TB minus 24,000 B upon GJ plus TB minus 36,000 A GJ equal to 0. So GJ is common, we can just remove it and we can simplify it. TBC plus TB times B minus 24,000 B plus TB times A and minus 36,000 A 0. This will give me TB A plus B plus A. This is equal to 36 plus 24 or 36,000 A plus 24,000 B. Let's substitute the values. A, B, C. A is 75, B is 125 and C is 100. And remember, these are in centimeter. So 36 75 plus 24,000 into 125. This will give me TB value as 36,000 into 75 plus 24,000 into 125 divided by 75 plus 125 plus 100. This gives me 19,000 kg centimeter, right? Yeah. Now TA can be calculated with the formula TA, like using the torsion equilibrium or moment equilibrium equation. TA plus TB would be equal to 24,000 plus 12,000 and TA would be equal to, this would be kind of 36,000 minus TB by TA would be equal to 36,000 minus 19,000. This would be equal to 17,000. Okay, kg centimeter. So now we have the like internal torque in the portion A and in the portion C, like in the portion OA and portion BC. In the portion BC it will be TB, in the portion OA it will be TA. Now if you want to calculate what would be the internal torque in portion AB, so if we try to go from the left convention, OB way, like if you want to calculate in AB, it will be so TPA would be equal to TA minus 12,000, and this would be around 17,000 minus 12,000, that is 5 kg, that is around 5,000 kg centimeter. So this we have calculated using following the left one. Like if you want to cross verify with the right, so TBA can also be written as TB minus TB minus 24,000, and TB comes out to be 17,000 minus 24, oh sorry, TB is 19,000 minus 24,000, and this would be around minus 5,000. So kg centimeter. So with this, the sign, like from right it would be some other direction, it would resist the direction as opposite to as from the left. Okay, so let us see this matches. So now we can say the portion A it would be 17,000, portion B it would be 5,000, in portion C it would be 19,000. So let's match and see. So portion A 17,000 matches to option C, then 5,000, then 19,000. Option C matches perfectly. So correct answer would be option C. Okay, I hope you can go through again through this. You can go through the video again and the lectures as well, the notes, and see how has it been calculated, and see that correct answer would be option C. Now let's move on to the next question, and probably this would be the last question for today's discussion session. So let's solve this. The question is, a steel shaft and an aluminium tube are connected to a fixed support and to a rigid disc as shown in the figure. Determine the maximum torque that can be applied to the disc shaft T if allowable shear stresses are 200 MPa in steel and 80 MPa in aluminium. The modulus of rigidity of steel and aluminium are 77 GPa and 27 GPa respectively. Okay, so as you can see in the diagram, uh, there is a steel shaft with a diameter 50 mm, and it's inside an aluminium tube with the thickness of 8 mm, and uh, and the given thing is uh, so allowable, or I'll just write TAN steel, it's 200 megapascal, and the tau A in aluminium, it's 80 megapascal. Other data which has been given is shear modulus, or the modulus of rigidity of steel, it's equal to 77 gigapascal, and that is 77 into 10 to the power 3 megapascal, and modulus of rigidity of aluminium, it's equal to 27 gigapascal, that is 27 into 10 to the power 3 megapascal. Okay, so the question asks what would be the maximum torque that can be applied to the disc shaft T. Okay, for that let's first write other data which has been provided. So okay, the diameter of the steel is given to be 50 mm, and outer diameter of aluminium is 50. It's already given, it's 76, right? So 76 mm, and inner diameter of aluminium would be 76 minus 2 times of 8, right? Because the thickness is given as to be 8, and this would be coming around 16. Uh, so we have already come to the last question for the today's discussion session. So you better go through today's recorded lectures and notes. Okay, so the question which we are discussing now is this question. Steel shaft and an aluminium tube are connected to a fixed support and to a rigid disc as shown in the figure. We have to find the maximum torque that can be applied to this system. Considering the allowable shear stresses are 200 megapascal in steel and 80 megapascal in aluminium. The modulus of rigidity of steel and aluminium are given out to be 77 gigapascal and 27 gigapascal respectively. So with that, we are just writing what all data have been provided. So so the diameter of the steel is 50 mm, outer diameter of the aluminium is 76 mm, and inner diameter of the aluminium tube would come out to be 76 minus 2 into 18, and that would be around 60 mm. Okay, now let us write the torsion equation. Torsion equation is T by J theta by L equal to tau by R, and if we see what all data have been given, so we can see that we need to use the first and third expression to find the maximum torque, and so that will give me T by J equal to tau by R. Okay. Now let us calculate okay, so theta would be same for both this system, theta steel and theta aluminium, because both are connected with the same disc. So when the torque is applied, same theta will come out to be in steel as well as in aluminium. So we'll use all the three expressions. So first we'll use the second and third expression. First use second and third expression for both aluminium and steel, and consequently we'll calculate the torque generating cause of the others. Okay, so let us write it. So that will be equal to, so first thing first, let us calculate the polar moment of inertia for both the system, steel as well as aluminium. So can write the aluminium as pi by 32 T for aluminium of 4 minus Ti, and this would be equal to pi by 32 76 4 minus 60 to the power 4, and this would come out to be so this comes out to be 200297.945 mm to the power 4. What about steel? That would be equal to pi by 32 d t to the power 4. That would be equal to pi by 32 into 50 to the power 4, and it will come around 613 592.315 mm to the power 4. Okay, so two things have been calculated. Now, as I told you, uh, theta would be same for both the system. Like theta steel would be equal to theta aluminium. Now, if I try to use the first two expression, that will give me T steel upon L steel upon G rather TL by GJ steel upon TL by GJ aluminium, and T steel LST would come out to be the same as aluminium. Okay, let me write it. J steel this gets cancelled out. Okay, G steel is 77. This steel is 613,592.315, and this is 27, I think. Yeah, 27 into 10 to the power 3 times this would be 2002978.945. But is still so it is still
सर
yeah.
सर सर मेरा कुछ क्लासेस थी इसलिए मैं क्लासेस अटेंड नहीं कर पाया था, तो आई थिंक इसकी रिकॉर्डिंग अवेलेबल होगी सर?
Yeah, sure, it will be available, because as you must have received links of the previous discussion sessions also, right?
सर उसी लिंक पे ओपन होती है?
Yeah, you got the spreadsheet, right?
नो सर.
uh, okay, I'll give you a link in the
नो
chat box.
सर. यस सर.
I'll give you link in the chat box. After, like, let me complete this question, then I'll give you the link for the, like, in the chat box, if it's okay with you.
ओके सर. ओके, थैंक यू सर.
Yeah, okay. So 613,592.315 divided by 2002,978.945 and into 77 divided by 27. So this is equal to 0.8736 T aluminium. So when the torque T is applied in the system, the torque taken by the steel system, it would be kind of 0.8736 the times torque applied in the aluminium system. Now like what should I say, let us use using yeah. So if my total torque T is this would be equal to torque steel plus torque aluminum, and if I substitute the values 0.8736 of T aluminum, so this will be T aluminum will come around to be mm, 0.534 of T, and T still will be equal to 0.8736 of this, that would be 0.466 T. Okay. Now let us use this second and third expression. No, let us use what we want to calculate. We want to calculate maximum torque, right? So we'll use the first and third expression of the torsion equation to calculate the maximum torque in the system. For that, mm, so we'll use the first and third expression, and that is T by G. Oh, sorry, J is tau by R, and uh, so if I use uh, J tau by R, uh, mm, so if I use tau max aluminum, T aluminum will be kind of tau aluminum uh, times J aluminum upon R aluminum, and this would be equal to mm, aluminum is 80 and J aluminum comes out to be 2002978 and 954 aluminum 945, and radius is say 50 sorry, maximum, so 76 by 2, 76 by 2, and it will come around 80 2 0 2 uh, 978.945 divided by 38, so it will come around 4216797.77. This is Newton millimeter. Now according to this, what will be, like, if my T aluminum is this, my T would be equal to so using this 0.534 uh, the aluminium is 0.3534 of this. So divide by 0.53534. So it comes around 7,896,625 Newton millimeter. If I use, like if I proceed through aluminium, okay, take the case of aluminium. When I take the case of steel, uh, so T steel is tau steel times J steel upon R steel, and this is, I think, uh, 200 200. This is uh, 613,592.315. 613,592.315, and radius of the steel is 50. So 50 by 2, that is 25, and this will be equal to 200 times 613,592.315 divided by 25. This will be equal to 4908,738.52 Newton mm. Consequently, torque corresponding to this, using this expression, so divide by 0.466, it comes out to be 10,533,773.648 Newton mm. So, comparing these two, like maximum design capacity for the aluminum is only this, what do you say, if I take it into kilonewton meter, uh, this would be 3 this would be around 7.89 kilonewton meter, and this would be around 10.53 kilonewton meter. So design capacity corresponding to aluminium, it's only 7.89, while steel would give me 10.53. But we, if you want to have sustain this system, so it will be lesser than this two. So correct. So the design torque of the complete system would be this 7.89 kilonewton meter. So this is the answer. It's quite a lengthy question, so please go through it carefully, and answer would be 7.89. Rest of the questions are uh, like it is similar to what I have already discussed. You just need to use the formula and just substitute it and you'll get it. You guys can practice. Okay, this is it for today. I'll just share the link for the video where you will get it. Okay, give me a second. So in this question, I have solved various types of questions that will cover most uh, different type of questions which can come or which can be asked in this topic, that is torsion, and you guys can go through the rest. Like I have also provided various other questions which are similar to what I have already discussed. So you try to do this, that will help you to do practice, and solve. You guys can solve the assignments easily. So go through this, go through the recorded video, go through the lecture notes. If you still feel any doubt, you guys can like post it. I'll try to uh, resolve your doubt like maybe in the next discussion session, or like I'll post it in the discussion forum itself. Okay, so I'd like to stop the discussion session for today here. If it's okay, can we wrap it up, Raj? And like go through the recorded lectures. That only I can say.
Okay, sir.
Yeah. Okay. Thanks for joining. Bye.
Okay,
Take
sir.
care.
Thank you so much, sir.